Okay. Okay. So I welcome you all again in our intellectual adventurous meeting. Today I'll talk about so this will be an introductory talk on group theory, not an introductory talk because we have been talking about group theory since the last year, but there we talked about different aspects, more mathematical aspects. But today I'll talk about more artistic aspects of group theory. So that will be so I've planned that I can give two talks on group theory and art, and this will be first of those talks. And today I'll talk about Frieze groups, as you will see. So today there will be less of math, but more of art. Okay, so this is the brief introduction and objective of this talk. So I'll say a few words about how group theory can be used to study art. I mean, I'll give concrete examples as to how we can use group theory for studying art. And in this two talk series, I'll first talk about this is first talk, Frieze groups. So which has one axis of translational symmetry, and the other one is the crystallographic groups. So these can also be for the 3D for the 3D case, but I'll primarily talk in the next talk about the 2D case. So that will have two linearly independent axes of translational symmetry. So today I'll talk about the first part, that is Frieze groups. So if you want to know more about these things, so I've taken some more. So this talk is based on a book on contemporary abstract algebra by Joseph Gallian, and it's the fourth edition, and it's in the chapter number 28. So this talk is going to be about Frieze groups. So let me talk about the Frieze groups. So Frieze groups arise in the case when we talk about one-dimensional axis of symmetry. So as you will see, what do you mean by that? Or you may have already guessed it. So these sorts of designs are used in decorative strips and patterns in jewelry. Oh, there should have been N as well. And now let's study these groups in detail. And perhaps we will also study about some of the algebraic properties. So this is the first case in which can someone guess what is happening in this case? So let's say you start with the black one as the, let's say, a unit or a design or a pattern, and what is happening to the other patterns? Can someone say? So here I've just made a translation. So starting from this, I have translated this to here, 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 and this to here. So as you will see, there is a way of mathematically saying about these operations. What exactly I'm doing. So this is first group, first of the Frieze groups. Second one is this, in which you can see I have taken some sort of reflection, but this is not just reflection, it's called as glide reflection, and we'll talk about that. Third is this. So here I'll talk more about these, but you first of all see all the groups in once at once. Okay, so fourth one is this, fifth one is this, sixth pattern is this, and seventh pattern is this. So here black shows, so that's the most fundamental unit. So if you do appropriate operation on that black unit, you will get these patterns as you will see next. So now I'll give some examples from architecture. So you see these kind of things, because this is going to be a talk in which I'll take only one dimensional case, but in the next talk I'll talk about the two-dimensional case. So so you have 17 sort of groups that take care of that of the 2D art. So in that case, you have two translational or other degrees of freedom. That in that you have two axes of symmetry. So these are some of the examples. So let's say if I consider this case, so this is perhaps easiest to understand. So you take just this basic thing here, and you just make a translation of this whole thing here in the positive x and negative x, and you can generate this. So this pattern is the most easy one to understand. And if you talk about this, so this and this has the same group of symmetry, and also this one. So you take this as the basic unit and you just translate it. in the x or in the negative x direction, and you get this. But this is a bit different because in this case, you're also having reflection. So what you're doing there, you are taking this as the unit, let's say this one, this as the unit. Oh, maybe this as the unit then, and then you make a reflection and then you translate it. Again make a reflection, you translate it. Again make a reflection, you translate it, and so on. And this is how you generate all these patterns. And in this case, so let's say this is the basic unit. You take a reflection, again take a reflection, again take a reflection, and then you keep translating them. So these are all examples of Frieze groups. So there are some more examples from Indian architecture now. So these are some of the examples, and this is an example from some Keshava temple. Perhaps I don't know the exact location of the temple, but perhaps it's somewhere in the southern part of India, and also here. So as you can see here, so this swan is just repeated in the x and the y. Sorry, in the positive x and in the negative x direction. So let's say you consider this as a swan, one unit, and then you translate it in the positive in the negative x one by one unit, by another unit you will get this. And if you do the same in the negative direction, or rather in this case positive direction, you will get this, then, and so on. And this, all these sort of patterns you can generate accordingly. So let me first talk about group F1. So as I said before, there are 7 such groups. So let me first talk about group F1. So this consists of only translations, as you will see. So let me denote X as the translation of one unit to the right. So then what it means, then X inverse would be the translation of one unit to the left. Okay. So then this group can be written as F1 equals X power n, where n is an element of Z. So n can be where Z is the set of integers. So n can be 0, 1, 2, 3, -1, -2, -3, -4. So in that way, it's isomorphic to the set of integers, because if you take n, because you can take n positive and n negative values, and it will generate one element, and as I will explain. Okay. So as I just said, this group is isomorphic to the group of integers, because any question?
Yes. Can you tell what is isomorphic groups?
Isomorphism is a okay. So let's say you have two groups. Let's say group G1 and G2. If you have a bijective mapping between these two groups, then these two groups are isomorphic. So bijective mapping means there is one-to-one and on-to correspondence. So in simple words, if I say one group is isomorphic to other, then they have exactly the same algebraic properties. So if I study one group, then I know about the properties of other group as well.
Okay.
Okay. So let's first do this study. So let's say I take this, let's say the pattern, and if I don't do anything to it, so it's just I'll keep it as such, and I don't do anything to it. So now let's try apply or let's try doing different operations to it. So first is I translate this by this quantity by x. So here I've chosen black color for the basic or the fundamental unit or the fundamental pattern or whatever you want to call it as. And then when I operate it by x, so this translates to this position. Okay. And when I again do that operation x, then it translates to that. So this distance is the same. So this distance and this distance is the same. So this is, I'm taking as one unit. And similarly, if you do it x power -1, so it translates to the negative x direction, and so on. Okay. So this is one case. So here I've taken this as the unit, and if you take, for example, this as the unit, let's say this one, so this is the pattern you generate. So it depends upon you how much distance do you want to put in between these basic units. So if you put them very close to each other, then perhaps it will look even better. But in order to understand it better, I have placed them a bit apart. Okay. So this is the group F1, and now let me talk about, oh yes, I think I was talking about this isomorphism. So isomorphism in that sense, because you see, when you have the set of integers, so and then you can also define a group operation on it. So in that case, 0 is the identity element. And then the inverse, so let's say inverse of 1 is just -1. So in that way, the set of integers can also be seen as a group. So this group F1 is isomorphic to the group of integers, because for every n, where n is an integer, there exists an element in the set of integers. And since the set of integers can be made as a group, and this is a group, therefore the two groups F1 and the set of integers are isomorphic. Okay. So now let me talk about group F2. So okay, so this is what you do. So now I talk about the glide reflections. So what glide reflections are? So glide means you first glide it in this direction and then you take the reflection. So then I'm considering these two operations in just one go. So when I'm writing G, I'm doing these two operations in one go, or rather I'm expressing these two operations by G. Okay. So what is happening? This moves in this direction. Let's say if you apply by G and then you take a reflection. So this is what the glide reflection does to this basic structure. Okay. So earlier we took only translations X, but in the present case for the group F2, I'm taking now the glide reflections. Okay. So this is what happens. So when you operate this by G, you translate it in this direction and then you take a reflection. It becomes this. And then for G square, you again operate it by G. So then you translate it in this direction and then you take again a reflection. It becomes this. And similarly, to get this, you operate by G inverse. Okay. So then it moves in this direction. You take a reflection, it becomes this. And then you again operate by G inverse. And then it moves in this direction and then you take reflection and it goes upwards. Okay. So so we will represent this group as F2. F2 is the name of the group, and this is how it's generated. So in group theory, we will say that this group and also the group F1 are generated by generators. So here G is the generator of the group F2. Okay. So this is just the basic language that we use in group theory. And okay, and also, so if you consider
Rahul bhai,
yes,
I have a doubt.
yes, please ask.
So if you yeah, this thing very we are very fortunate to have learned it in some crystallographic this thing, na? Glide plane and screw axis and all that.
Mm-hmm.
So since you are discussing along one dimension only,
Mm-hmm.
so if we can consider a motion along one dimension,
Mm-hmm.
where the where the translation is generated by the linear momentum. So can we consider that the linear momentum belongs to a Frieze group or something as such? Have you seen, or can you see that thing along this way?
So first of all, linear momentum can take continuous values, but these are all discrete groups.
But quantum mechanically it won't, na?
No, so what I'm saying is in this case, because there are discrete translations and reflection operation is also discrete in some sense. But if you say about momentum,
Yes. So
so then the momentum can take continuous values. So that
but what if we consider the quantum mechanical aspect? Momentum doesn't take continuous value, na? Or does it take?
For a free particle, it takes continuous values. For example, for a free particle, it takes continuous values.
Let's suppose P is equal to h cross k.
Okay.
So and h cross is anyway is a discrete number.
So
And
then it may be.
let's.
Okay, then in that sense it can be, because if you
No, I was just thinking. I don't know.
no in that case
I
it's
haven't
applicable,
heard this. I was just asking.
because if the momentum takes discrete values, then it will only translate to discrete places. So then in that way it's correct, but not in general, because
Okay.
momentum can take any I mean, since momentum takes continuous values, it will continuously move these things. So so if you want to think of momentum as the generator of translation, what you would like to picture it as, that this goes
Yes.
very close to this this thing's location, and then even very close, it moves very how to say that. So and you will not picture it as, so from here it directly went there, so it moved through very small
Right.
gaps. If you consider momentum, yes.
Small gaps. Okay.
Yeah. But if it is continuous, then it will of course translate this thing to discrete places, then it's also correct. Okay.
Okay. Thanks.
And any further question? No. Okay. So
No, it's fine. I got it.
okay. And also you can see a similarity between this group F2 and group F1 that we saw in the previous slide, that it is also actually generating these translations. So there the translate, but not for all values of n. So if you take, let's say, only even powers of g, n equal to now, let's say this one, g square, g power 4, g power 6, g power 8, then it's again translation only. So there is no glide reflection now. There is only translation, because if you see, if you directly operate this by g square, then you get this. So it's basically a translation, not a glide reflection. So in that way, so what we discussed in the previous slide already contains in this. So F1 contains in F2. So in that way, F1 is a subgroup of F2.
I just want to ask one small question. In the third point, this like the F2 equal to G raised to power n.
So
here
sorry,
Z
n is Z,
is
n is Z, n is Z. Sorry, galat ho gaya.
Okay.
Thank you.
Okay.
Okay. So and then if you take that, so in the previous slide, I also took one example of an ornament. So if you do these same operations on an ornament, this is what you get. So this is the pattern that you will generate. Oh, so okay, let me go to the previous slide. Yes. So then, so it's basically what I've done above. Okay. So this pattern will be generated, and again, if you put them very close, then it will perhaps look more beautiful. Or if you want to just maybe translate it in the y-axis, that's up to you how close you want to put them together. So if you put them really close, then they might create even beautiful pattern. Okay. Now the third group, that is F3. So I mean, so they don't have any specific name, but then you can identify based on the operations that they do on this basic unit, this unit, black unit. So based on that, you can identify that what sort of group is that. So let's talk about group F3. So this is a combined effect of both reflection and translation, as you can see it very clearly from here. Okay. So let's say I denote the translation by X again, as I have been doing till now, and also the reflection about the vertical axis by Y. Okay, Y and X. So now you have two generators of this group. So till now we had only one generator, X or G. So G was glide reflection and X was the translation. But now we will have two generators, X and Y. They will generate the group together. Okay. So so I'll explain what is happening here. So then we can write this group as X power n, Y power m, where where m takes only two values, 0 and 1, and n again takes an integer value, positive or negative, -1, -2, -3, -4, 0, 1, 2, 3, 4, and so on. So specifically, these are some of these elements. So let's say some of the elements would be X, Y, Y, and for every such element, there will be one operation. So let's say the operation that does something to this black element. So for example, if you consider Y, so Y is just the reflection about the vertical axis. So that would mean that this black becomes this red. Very easy to understand. And now you can also perform translation on this thing. So you just operate it by X. So if you do that, this comes here as it has been. So this comes here, and if you perform, so and now that's sort of convention that we use in math or in physics also, that if let's say if you write X, Y, then it means that Y is performed first and X is performed later. So this is just a convention. So now if you perform this, so this has been here. Now if you perform this by X, so this will translate to this position, because X is translating the basic unit, this, and Y is reflecting it about the Y axis. Is this clear? It should be. Okay. So now I can use this this idea and can get what sort of pattern will it look like for the ornament that I've been showing all the time. Oh yes, so I've talked about this already. And yes, there's one more thing. So here I've taken the axis, the symmetry axis to be this. So let's say, no, not a, let's say. So I have made a reflection about this axis, but I could have chosen any other axis. So the pattern would have changed in the sense that it would have been that this would have been here or some other, but overall the pattern would have been the same. I mean, so what is happening here? Instead of just one unit repeating, you have two units. So this is just getting repeated. So this comes here, and if you just translate this by one unit, you get this, and you translate this by one unit, you will get this, and so on. So and this is what you get for that ornament. So this is the pattern that will generate. And again, you can put them very close, and then it will look even more beautiful. I've not tried that, but it should be very easily doable. Now the fourth one. So fourth one is a bit tricky. Okay, so fourth one is a bit tricky because it involves first translation that we have been talking about from the group F1, but it also involves a rotation. So let's say you consider this as the point P. This is your point P, and you rotate this thing by 180 degrees, either this way or this way. You will get the same. Okay. So if you rotate this, so are you able to understand that you rotate this thing about this point so that it comes there like this, or anti-clockwise for that matter? So it is still the same. So then you say that that this group is generated by both X and R, where X is the translation and R is the rotation about this fixed point. So this point lies here, and for this one it will be here. For this one it will be here, and so on. Okay. So okay, so let's do it for so again the typical sort of elements would be XR, R, X square R, X inverse, or maybe X power 10 times R, or XR, for example. So, and because since it is a group, so that's why the two elements will again combine to give some sort of other operation, because it's a group. Okay. So let's say what happens to this. So if I just do R on this, it will rotate this thing about this point P. So it will become this. And when I operate it by X, it will translate it to this point. And when I operate it by X on this part, it will come here. So this is how you will generate this pattern. And again, if you use these ideas on the ornament, then you will get this sort of pattern. So as we have been seeing, these all patterns are different. As you should be able to see, all these patterns are different.
I have one more question.
Okay.
So you are saying R is rotation here. So it should be like some angle or what? Because I don't understand the meaning of R square or R cube.
R square is the same as no rotation, because if you rotate 2 times by 180 degrees, it will again become the same. So what I'm saying.
Okay, so means.
So what I'm saying is, let's say you consider this point P, this one, this red dot, and you rotate this quantity by 180 degrees, this one, so it becomes this.
Yes. So the power 2 means you are rotating again, and then power 3 is rotating again, so that it is going like that.
Yeah. So but if you rotate it twice, it will be at the same place. It will become the same. So R square is 1 just.
Okay, and cube is again equal to 1 rotation.
Yeah, R cube is equal to R, exactly.
Okay.
So अच्छा मैंने यहाँ पे उल्टा कर दिया. So it should have been n only. So there I've already written that n can only take two values, 0 or 1. If you take 2, for example, and as 2, then it is same as 0, r power 0. Or if you take r cube, it is same as r. Okay. So and then you have a name for this. I mean, so this is how you would say in group theory that this group F4 is generated by two generators X and R, and the order of R is 2. This is how you would say it. Okay. So let's talk about group F5. So group F5 is perhaps the most complicated group, but yeah, and it also generates very beautiful pattern as well. So then this group is generated by first glide reflection. So we have seen an example of glide reflection in group F2, and a rotation R, so which we saw in F4 of 180 degrees about the point P. That's here. Okay. So again, it will have these sorts of elements: G inverse R, G square, G power 10 R, for example. Okay. And different elements of the group will perform different sort of operations on this, and it will lead to different results. So this group is generated as this. So here, and again, n can be negative or positive, -1, -2, -3, 0, 1, 2, 3, and so on. And m is just 0 and 1. So now what you do? So let's say if you just take r, so r is again the same operation. You take this point P and you rotate this quantity by 180 degrees about this point. So you will get this. Okay, so you will get this. But now if you do the glide reflection, what it does? It will first of all glide it here, and then you take a reflection. So that's how the glide reflection works. Is it understandable? Or should I explain it once more? Is it okay?
Once more.
Okay. So what I'm saying, so let's say you start with E. That's the basic structure you have. And then you make this rotation about this point P by 180 degrees. You will get this. That's fine. And now when you make glide reflection, so what it does, you will slide it here at this point and then you reflect it. So you will get this. And this is the consequence of glide reflection. Now what happens when you perform glide reflection on this quantity? So what will happen? So first of all, you have to translate it to this point and then you take a reflection. So this becomes GR. Now is it clear? And similarly for other elements.
Yes.
Okay, fine. So, and then it also has a vertical reflection symmetry, as you can see it from here. So here, and then it will continue. And oh no, yeah, here, and here. So it will continue like that. And you can also see that this pattern will also repeat. So this pattern will come here. This pattern will come here. This will also repeat. So again, it has translation symmetry. So as I've been talking about this since in the beginning, that this has only one axis of translation symmetry. For example, if you take this pattern and you translate this by this to this place, it will be the same. It will be identical. But then we will talk about the crystallographic groups in the next talk, and that will have two axes of symmetries, as we will see in the next talk. So then the same ornament, as we have been talking about, will now take this form when you perform, or when you operate this by on sorry and when you operate F5 on this basic unit, then you will get this sort of pattern. Now group F6. So okay, can anyone guess what is happening here? So let me not tell you anything about the group first, but let me ask you what is happening here. Can someone tell me? अरे कोई तो बताओ यार.
Hello. Hello.
हाँ, yes.
Rahul bhai.
Tell me.
This is first one is glide E.
Translation.
That basic unit. First translate and then reflect it.
Exactly. Translation and reflection, yes. So then what you're doing here, you are translating this to this place. So that will but or rather that is equal to the operation of x on this quantity. So this comes here, and then you take a reflection. So this comes, so this is this. So, oh no, that's wrong. First, let me see whether it's no y बाद में आएगा. But then okay, fine. In this case, x and y is equal to xy is equal to yx. So there should not be any problem because here x and y will commute. So yeah, fine. xy is equal to yx. Okay, so again, this can be written in this form. And yeah, as I said, because xy is equal to yx, because you can first translate and then reflect, or you can first reflect and then translate. The result will be the same. So in that way, x and y commute. Okay, so in that way, this group is isomorphic to Z cross Z2. So what does that mean? That Z2 contains only two elements, 0 and 1, and that is addition modulo 2. So if you so what is the operation of 1 plus 1? That is 0. When you add, or you all are familiar with the modular arithmetic. Are you all? Do you know what modular arithmetic is?
No.
Okay, so for example, so modular arithmetic will give, so it's like that. Let's say if I say 5 mod 3, so I want to determine what is 5 mod 3, then I first divide 5 by 3 and we'll see the remainder. Okay, so remainder in this case is 2. So 5 mod 3 is equal to 2. So I'm just looking for the mod, or and we use this operation very much in Python and C as well. So mod is mod will just give you the remainder. Okay, so and similarly, and the results we
So
have
that,
results in, sorry.
So that means we are taking mod of anything, we call it modular arithmetic.
Not mod of that sort, not -1 mod is equal to 1, not that mod.
No, that remainder.
Yeah, exactly.
So only that operation comes under that modular arithmetic.
Yeah, so not that operation comes, but then operation related to modular operation. For example, let's say if I have two integers x, y, then x plus y mod p is equal to x mod p plus y mod p. This is modular arithmetic.
Okay.
In that way, कि remainder कैसे calculate कर सकते हैं, ठीक है ना, ये है. Okay, so so then if you consider Z2, then it's so the group operation is addition modulo 2. So so it has only two elements, 0 and 1, this Z2. So then 1 plus 1 mod 2 is 0. So you see the same sort of thing is happening here, because if you take the reflection twice, then you get back as no reflection. So in that way, I mean, I will not, I'm not going to prove that it, and it's also not very difficult to prove it, but then you can understand it intuitively. So why? So Z is this because of this, that n can take any integer values, and m is because of this, that since Z2 have only two elements, 0 and 1, and 1 plus 1 mod 2 is equal to 0. And the same sort of thing was happening in this case, that if you take two reflections, then you again get back the then it is the same as no reflection at all, in that way. Okay, so and this is what happens with this ornament when f6 operates on this black thing. Finally, this seems also very pretty. So finally it's group f7. So now you have three operations in this case. You have vertical reflection, horizontal reflection, and also the translation, all of these together. Okay, so you have x as the translation along x-axis, y as the reflection about the vertical axis, and z as the reflection about the horizontal axis. This is what you get. So, and it should be very easy to understand how it is happening. So let's say first, or you may start with any sort of translation, for example. So here, this black, when you translate it by some unit, then it goes here. And again, this comes here when you operate it by x inverse. Okay, and then you can also take its reflection about the vertical axis. So that means you operate this quantity by y. So this is the reflection. And you can also take its reflection about the horizontal axis. So for that you have to operate this by z. So then you will have to take the reflection about this axis. So you will get this. Okay. And then you will have various different elements. So this is how again this group is generated. So now since you have 3 generators, x, y, and z, this is how it groups. This is how this group looks like. And again, you will have elements of the sort like x square, y, z, x square, maybe y, x square, z, and so on. Okay, and you can accordingly figure out the operation corresponding to a group, a given group element, and this is what you get. So and then you can see that now this is the unit that gets repeated. Okay, so this is what is getting translated. So this whole unit here, here, and here. Okay, so I thought and it's not that difficult to identify it now, because wherever you see the symmetry about the horizontal and the vertical axis, you can very quickly identify that it has to be F7. So it's not that difficult to come up with an algorithm to identify which sort of so whenever you will see now patterns on some place in some temples or any old building perhaps, then the first question that will come to your mind is, which symmetry group is this? Since you know how to analyze symmetries, at least for the case when you have one axis of translational symmetry. So and also the composition of 2 elements. So I actually have not talked about this, but since these are groups, so groups have properties. If you take 2 elements of the groups and then you compose them together, then you get some other element of the same set. Okay, so and it's again very easy to see what is the operation of, for example, in this case, let's say what is the operation of what is this equal to, xy times x square z, for example, this one, and that you can identify very easily by seeing what is the effect of this operation xy times x square z on this black leaf. So then it's very easy to identify. So and this is what happens. So here I'm again just doing the same operations on this black thing over here, and this is what you get. And this is the axis of symmetry, the vertical one, and then I take the reflection about the horizontal axis as well, and it should be very easy to identify. Okay, so now the epilogue. So we have talked about 7 Frieze groups. So and these corresponds to only one axis of translational symmetry. But in addition to this, there are addition 17 discrete symmetry groups. So which I will talk about in the next talk. So which leave a design. So in this case, the design was invariant when you make a translation in the, let's say, x-axis, but then there are also 17 discrete symmetry groups which leave the design invariant when you make a sort of combination of movement of along x and y axis together. Okay, so that we'll talk about in the next talk. So I really thank you for your attention. So if you have any questions, you can ask them now.
I have already asked.
Okay. Yeah, because today's talk was very easy to understand. So I won't be surprised if you won't have any question today, because today's talk was very easy to understand, I would say. Okay, so if there are no questions,
I have only one.
Okay, yeah, please go ahead.
In F7 there was some mistake na in the down one.
F7 isme?
Yeah, the second line x z inverse y. It should be x inverse or it is correct?
ये वाला
इसके बगल वाला.
ये वाला. अच्छा, let me
It
check.
should be x inverse or
just a second. Oh, z x inverse y. ठीक है. मतलब इस पे किया ना तो
इनवर्स या
z x इनवर्स y, ठीक है, ओके।
ये बॉटम वाले एक्स इनवर्स होना चाहिए, राइट? एक्स इनवर्स जेड इनवर्स वाई, राइट?
नहीं z इनवर्स नहीं,
नहीं
z
नहीं,
x इनवर्स y,
बॉटम वाले में।
ये वाला ना।
हाँ हाँ, ये वाला
हाँ, z x
कुछ
इनवर्स
भी
y,
एक्स।
ये ऑपरेशन इस पे किया ना तो ये वाला लिया, इस यहाँ पे
हाँ
इतना हो गया, इस पे z से करूंगा मल्टीप्लाई तो ये आ जाएगा।
हाँ, सो
ये
एक्स शुड बी इनवर्स।
हाँ, तो ये ऐसा होना चाहिए था, z x, ये होना चाहिए था ये, ठीक है, ओके ओके देन। सो अभी किसका टर्न है अगली बार?